My name is Claire Tomlin, and this is the 6th module in a series that we're doing for the course EE221A, Linear System Theory at Berkeley. And today's module is about how a matrix representation of a linear map changes when you change the basis of the domain or the codomain or both. Last module, we constructed the linear map itself, we constructed the matrix representation given the linear map and between the finite dimensional vector spaces and the basis. And so now we're going to ask the question, once you have the matrix representation and you change the basis, how do you quickly figure out what the new matrix representation should be without having to go back to the beginning and reconstruct that matrix representation? Okay, so we'll call it change of basis. And what I like to do here is to keep a picture in my mind of the spaces and the corresponding bases and then the map representation. So I'm going to have here, and I'll draw it, and I'll try to keep as much of this on the screen as possible. So I have, and we'll use the same notation that we always have, that we have our space U and our space V, and a linear map A, which takes the domain to the codomain. And I'm going to now look at another copy of U and V. Okay, so I've got U and V, and I've still got my linear map A here. Okay, so I'll choose a basis for U and V. So let's use the same notation that we've been using in these modules all along. So let U be an n-dimensional space. So we'll use Ui as the basis vectors for U here, and they have corresponding coordinate elements xi. Similarly, we'll use Vi for the basis, and eta I for the coordinate vectors over in the codomain. And as we constructed last day, or last module, that linear map has matrix representation A. Okay, so up here, we've got these same spaces, but let's think about different basis vectors. So we'll use Ui bar to represent the basis elements of U, and xi bar to be the corresponding coordinates, and then Vi bar and eta I bar. Okay, so we'll call over here, we'll call the matrix representation of the linear map A with respect to these basis elements capital A bar. So given A, how do we construct A bar directly? That's the question. What we're going to do in this module is show the construction of that change of basis for vector spaces which have basis vectors in Rm or Rn. This methodology works in general for more general vector spaces, which are finite dimensional, but which they're not necessarily Rn or Rm, and we'll see how that works. But for simplicity, we're going to assume that the vector spaces U and V are Rn or Rm respectively. Okay, so let's start off with a vector x in our domain, U. And so x has a coordinate representation with respect to the basis elements U bar as well as the basis elements U. So we can write it as xi1 U1 plus xi2 U2 plus xn Un. And I'm just going to rewrite that. So now these Ui's are vectors in Rn. And so I'm going to write that in terms of a matrix whose columns are U1, U2, up to Un. Okay, so this is an n by n matrix whose first column is U1, whose second column is U2, and whose nth column is Un. And I'm going to multiply that, post-multiply that by the vector xi, which is just the n-dimensional vector whose elements are the coordinates, xi1 up to xn. Now, I can also represent x as in terms of the bases u bar or ui bar and the coordinates xi bar. So that tells me that I can find a matrix transformation between the coordinates xi and the coordinates xi bar just by equating these two right-hand sides. So therefore, u1, u2, so remember this is a matrix whose columns are the basis vectors. Xi is equal to u1 bar. Similarly, columns are the basis vectors. Since these are basis vectors, they're linearly independent, which means that both of these matrices are invertible. And so we can construct a relationship between xi, this implies that xi is equal to some matrix P times xi bar, where P is simply this, the inverse of this matrix pre-multiplied by this matrix here. u1, u2 up to un inverse u1 bar up to un bar. And we can do the same thing for a vector over in our codomain. We can write it in terms of these two different bases and the corresponding coordinate vectors. And so we can derive a representation of eta bar with respect to the coordinates eta. So we'll call that matrix Q. And here, if we do the same construction, we find that Q is equal to, and here I've got eta bar in terms of eta, so this is going to be V1 bar Vm bar inverse V1 up to Vm. Okay, and again, these are vectors in Rm. There's m of them. It's a basis, so they're linearly independent, so this matrix is invertible. Okay, so I said that we were performing this change of basis for vector spaces, for matrices representing maps, linear maps between vector spaces, where the vector spaces are Rn or Rm. And you can see why I needed that here. I needed to be able to basically invert this matrix. So I needed it to be an n by n matrix and invertible. But all I really need is, in order to construct this relationship between the coordinates with respect to one basis and the coordinates with respect to the other, is I need a bijective relationship between the coordinate vectors. So in terms of this map here, all I really need is for that map to be bijective. And I have that automatically for finite dimensional, for the kind of finite dimensional vector spaces we've been dealing with, if these are bases and these are the corresponding coordinate vectors. Okay, so I have a relationship between xi and xi bar. So I can actually go back to my diagram here, and I can say that if I take the vectors xi bar and I pre-multiply by the matrix P, then I get the coordinates xi. And similarly, if I take the coordinates eta bar, or sorry, eta, and I pre-multiply by the matrix Q, then I get the coordinates eta bar. Okay, so that gives me basically the rule for transforming between the matrix representation A and the matrix representation A bar. So if I look at these equations here, let's just pull out the ones we need. So I have a relationship, the relationship between the corresponding coordinates for two different bases. And now I can think about how to precisely construct A bar from A. So I'm given A, and I want to find A bar. What is A bar? Question mark. Well, I know from our previous module on matrix representations of linear maps that eta is equal to A times xi. So that's how I constructed, that was within my construction of the matrix A. And now I also have these relationships here. So eta is equal to A times xi, but xi is P xi bar. So this is just A P xi bar. And then eta bar is equal to Q eta. So that tells me that eta bar is equal to Q A P xi bar. And so this here describes the matrix representation of the map A with respect to coordinates, with respect to bases U bar and V bar, with coordinates xi bar and eta bar respectively. Okay, and the coordinate representation is unique, so that tells us that A bar is actually given by matrix multiplication QAP. And we can think about this diagram here. If we started here, we could have come over here using matrix multiplication or matrix multiplication of coordinates A, or we could follow the matrix multiplication by P and then by A and then Q. So we basically can reconstruct A bar by following this arrow here or by following matrix multiplication by P, and then by A, and then by Q to end up in the same place. If the spaces are the same, so now I've looked at spaces U and V, but suppose I now consider this space over here to be U. So I look at two copies of my domain, or my codomain is equal to my domain. And I use this basis over here. So this basis I'm going to use for the domain and the codomain, and this basis I'll use for the domain and the codomain. Then Q simply becomes P inverse. And the matrix representation A bar is simply P inverse AP, which is fairly standard when we think about a similarity transform. In fact, this is a very general representation of a similarity transform between matrices, that these matrices have a lot of very similar properties, as we're going to see soon. But how we've constructed them now is just that given one matrix representation of a linear map, we've been able to construct a new representation of that linear map for a new basis, given the transformation between coordinates of those corresponding basis elements. Okay, so this is called a similarity transform. I think that it's very useful to keep this diagram in mind because it helps us think about what spaces we're looking at, what basis vectors we're looking at, and what the corresponding matrix representations of those maps are. I mean, P and P inverse are actually matrix representations of linear maps. There is a linear map, we could call it script P, which takes elements of U to elements of U. Given these bases, that gives us a matrix representation P. So it's a very general notation, and this diagram helps us to keep in order the corresponding bases and coordinate vectors. Because we could think about having a domain and a codomain, and we could think about changing the basis for the domain, but not changing the basis for the codomain, and asking then what is the corresponding matrix representation. So it helps us clarify and keep a very general picture of what's going on. So to conclude today's module, let's do a fairly simple example. And this example will be on, we'll think about a linear map which maps R3 to R3. So let's keep that diagram there, and let's draw the example. So A maps R3 to R3. So that's my linear map, map A. And I'm going to consider two bases. The first one we'll call basis elements B1, B2, B3, and I'll make that the standard basis. So 1, 0, 0, 0, 1, 0, 0, 0, 1. the standard basis elements in R3. And I'll choose another basis, vectors C1, C2, and C3. And let's just make that a simple variation on the standard basis. So 1, 1, 0, 0, 1, 1, 1, 0, 1. Okay, so clearly they're both bases for R3. And now let's think about this map A, and suppose you had the following information, that A takes the basis element, so A maps B1 to, we'll just choose a particular vector. A maps B2 to, let's say it's 0, 0, 0. And A maps B3, so again, this is the linear map notation. It maps it to 0, 4, 2. So you have information on how the linear map operates on the basis vectors B. And so the question is, write down the matrix representation of the map A. Well, your first response should be, I can't write down the matrix representation until I know which basis to use. And we've got R3 as the domain and R3 as the codomain. So I could choose basis B for the domain and codomain, or C for both the domain and codomain. Or I could choose B and C, or C and B. So there are different possibilities of what that matrix representation is. If we chose B, so suppose we were looking at copies of R3 with the standard basis in both of them. Then it's fairly simple. Just from inspection, you can construct or you can reconstruct what the matrix representation of the linear map A is with respect to these bases, the basis B. It's just going to be a matrix in this case. So in this case, the matrix is just going to be, the columns are just going to be the values of A of B1, A of B2, and A of B3. And that's because I just use my construction rule for the matrix A, which is that A of Bj is the jth column is A of Bj written with respect to the Bi's. So in this case, -2, 1, 0 written with respect to the standard basis elements is just, 2, -1, 0 written with respect to the standard basis elements is just 2, -1, 0, etc. So now if we had to change the basis, so suppose I change the basis over here to C, then what's my new A? Or suppose I made them both C, then what's my new A? So those are the kinds of questions that come up here. But keeping this diagram in mind and always thinking about the copies of the spaces with the corresponding bases helps you keep the correct matrix representation intact. Okay, so in summary, today we've talked about, given a matrix representation of a linear map between finite dimensional vector spaces, how do you construct the new matrix representation when you perform a change of basis? And we did a simple example with some extensions that you can try on your own.